Great, it's great to be here. So I'll be giving a tutorial on algorithmic aspects of inference more broadly. So this will be the first in a four-part tutorial, which is really about exploring some of the issues and problems at the intersection between algorithms, machine learning, and statistics. So what I thought I'd do for the first one is tell you a story about learning a very natural family of mixture models that's going to help me illustrate some of these themes that are going to come up again and again about how algorithmic goals can sometimes be at odds with statistical goals. So I'll tell you more about that in some of the other tutorials on things like tensor decompositions, linear inverse models, and then community detection. But I'm going to try and keep things simple and focus just on something called disentangling Gaussians for the time being. Before I even parse what the title means, let me explain what Gaussians are for those of you who haven't seen them before. So Gaussians are distributions. In fact, in one dimension, they're defined by just two parameters, the mean, mu, and the variance, sigma squared. A Gaussian is arguably the most ubiquitous distribution in all of statistics. It comes up again and again. And in fact, around the mean, that's its maximum value, and its variance describes how quickly it falls off as you go away from that maximum value. And what the main reason is underlying why this distribution arises in so many settings is in large part due to things like the central limit theorem. That tells us that if we take independent random variables x1 up to xs, that under fairly tame conditions on these random variables, if we take their sum and normalize it appropriately, then that converges in distribution to a Gaussian. So I'm not going to need precisely what this notation means, but it already gives you a hint about why the Gaussian comes up in so many different scenarios in modeling. Because you can think about modeling the heights of individuals. You have to be careful because you should first segregate the population to be, say, only males or females. But then things like height are known to be controlled by at least 12 genes. And if you think about actually how they affect height, then it's very well approximated by Gaussian. It's also used to model things like the velocities of an ideal gas, and also in some ecological applications like modeling things like annual rainfall. So this is why the Gaussian shows up in so many settings, is the central limit theorem. But actually there's another story that I'd like to tell you, which is going to be the main focus of this talk, is that the Gaussian isn't always the answer. So in fact, there was a very famous statistician named Karl Pearson, who was one of the founders of statistics. So back in 1894, he was very interested also in biology and evolution. And there was a particular species of crabs called the Naples crab that inhabited the region around him. Now what he did was he took thousands of samples from this crab population, and for each one of these crabs he measured some physical characteristic. In this case, he measured the ratio of the height of the crab divided by the circumference of its head for some reason. And what he believed was that what he would get if he plotted the frequency of occurrence of different values would be well approximated by a Gaussian. Now this is the density function that he got, the little jagged thing there. Now it surprised him because it wasn't a Gaussian. In fact, it wasn't even symmetric around its maximum value. So he was quite puzzled by this, but what he offered as an explanation was that maybe the Naples crab was not one species of crab, but rather two. And that the density function he observed could be explained as a mixture of two Gaussians. So this is actually the problem that Pearson set out to try and solve back all the way in 1894. I'll tell you some of the more remarkable things that actually happened just in this paper as we go along. But let me get into some details about what Pearson did, and then I'll use this as a leaping off point to talk about the interaction between algorithms and statistics. So, what is Pearson trying to solve? So what he believed was that he was being given samples from a mixture of two Gaussians. So I'll use f of x to denote the resulting density function. And all it is that density function of a mixture of two Gaussians is nothing more than the convex combination of the density functions of its two constituent Gaussians. So I'm going to use W1 throughout this talk to denote the mixing weight. And so what this means then is that if that's the density function of f of x, we can generate a sample from this as follows. We take a coin, which is heads with probability W1, and we flip it. And if it comes up heads, then we take a random sample from the first Gaussian and we output it. And if instead it comes up tails, we take a random sample from the second Gaussian and we output that. So Pearson set about this problem of, given what he believed were samples from a mixture of two Gaussians, can you actually learn the underlying density function? And in fact, this density function is characterized by just 5 parameters. The mixing weight, W1, which is the bias of that coin, mu1 and sigma1 squared, the mean and variance of the first Gaussian, and mu2 sigma2 squared, the mean and variance of the second Gaussian. So what it means to learn the density function is, certainly it suffices to learn good approximations to these underlying parameters. So this was Pearson's question, is in this idealized setting, can we actually learn the parameters approximately given enough random samples from F? And what was actually remarkable about this is, if you've ever heard of the method of moments, this is where it originated. So in this paper in 1894 is where Pearson invented the method of moments, was to solve this problem. And I'll tell you a little bit more about what he did. So it's often referred to as Pearson's 6-moment test. Underneath it all is the following crucial observation. This is what everything rested on to get the method of moments working. As we can think about these 5 unknown parameters, which sometimes I'm going to note as the vector theta, which is a vector of unknowns. Well, the point is, what you can do is you can take a random sample from f of x, the mixture of two Gaussians, and you can compute the value of x to the r. That's often called the raw moment. And the crucial observation underneath Pearson's approach was that whatever that quantity is itself a polynomial in the underlying parameters that we're trying to learn. So this is very simple in the case, for example, of r equals 1.
For every r.
Yes. For r equals 1, for example, then we're computing the expected value of x, so the mean of the entire distribution. And that's nothing more than the weighted average of the means of the two constituent Gaussians. So it's W1 mu1 plus 1 minus W1 mu2. A similar thing happens for r equals 2. You have to be slightly careful because that's not the variance, because we haven't normalized it to be around the mean. So instead, it's again the convex combination, a weighted average of the expected value of x squared of the two constituent Gaussians, except now the expected value of x squared from the first Gaussian is mu1 squared plus sigma1 squared. And I can write out the third one just to show you proof by intimidation that at some point these polynomials get a little hairy looking. It turns out that they're actually a nice family of polynomials, but that's not important, and I've clearly run out of space on this slide, so I should stop here and just assert the claim. But the important thing is now, let me give that polynomial whatever it is. It's not only a polynomial, it's a polynomial that you can explicitly write out very easily. And let me call that polynomial MR of theta, because it's going to play a crucial role in Pearson's approach. So now we have a very natural approach, is that we can actually estimate the left-hand side of this given random samples. That in turn gives us a polynomial constraint on the underlying parameters that we'd like to learn. So what's Pearson's approach now is you take a bunch of samples. In fact, he did this on his vacation, so that says a lot about what he likes to do on vacations. And all you do is you take the empirical average over those samples. So you look at x sub I as the ith sample, and you take the empirical average of xi to the r over your set of samples. That's your approximation to the left-hand side. And I'm going to call that m tilde sub r because it's not exactly mr, but it's something that converges to it as you take more and more samples. And the idea is that we just set up a system of polynomial equations. We had 5 unknowns, so why not set up a system of 5 polynomial equations? Now, the amazing thing was that actually he did this. So he set up this system of polynomial equations, and he solved it by hand in 1894. It's amazing. And in fact, if you think about it, there's not just one solution. This isn't like solving linear systems where you get just one solution or you get a family of solutions given by a subspace. In fact, you find many solutions to the system of polynomial equations. Each one is a simultaneous setting of the parameters that together would explain the first 5 moments. So some of these were clearly nonsense. For example, some of them had things like a mixing weight that wasn't bounded between 0 and 1. Sometimes they had a variance that was negative. That's also impossible. So he crossed off all of those roots, which didn't correspond to solutions he was looking for. But he still had more than one reasonable solution that explained the first 5 moments. And so what he did was he used the 6th moment as a tiebreaker. Each one of those remaining sets of parameters yields some analytic prediction for what the 6th moment would be. You just compute m6 of theta, and you choose among those candidate roots whichever one is the closest to what you actually observed for the 6th moment. That's Pearson's 6th moment test. This was the origin of the method of moments.
So you can't always make, for example, if mu1, mu2, and sigma 1, sigma 2 are equal, then no matter what you do, every relative value of w1.
We'll get into that later. So we'll get into that. So actually, that's a good segue. There are a number of issues with that, the least of which is that. So we'll get to that one too. But actually, this paper had an incredible amount of foresight because there are a lot of issues with the 6th moment test. Yeah, it worked in that one specific case and seemed to produce good answers. But there's some conceptual questions that we could ask about how well does it actually work. So in fact, in Pearson's original paper, the following quote is attributed to George Darwin, who I'm told had a famous father. In any case, so what he asked was, given the probable error of every ordinate of a frequency curve, what are the probable errors of the elements of the 2 normal curves in which it may be dissected? So Old English aside, what he's actually asking is a fairly modern question, right? Which is, if you think about it, these m tilde sub r's are only approximations to the underlying moments. They're very good approximations, but when you take less than an infinite number of samples, you haven't computed the moment perfectly. So inevitably, you have errors on the right-hand sides of your system of polynomial equations. If you have errors on the right-hand side, how does that propagate into errors in the parameters that you actually find? So how stable are polynomial equations to perturbations to the right-hand side? In fact, this was the question that Darwin foresaw. There's an even more fundamental question, which is, even if I gave you the right-hand sides perfectly and you computed them using an infinite number of samples, there's still an even more basic and more fundamental question, which is, why in the world should a mixture of 2 Gaussians be determined by its first 6 moments? So why can't there be 2 different mixtures that produce exactly the same first 6 moments that no matter how accurately you get the right-hand side can't be told apart? So we'll get to Anoop's question when we attack this latter part, but my main goal is actually to address these types of questions. And let me actually take a more modern view from theoretical computer science, where let's quantify what our problem really is and try and understand not just a heuristic that seems to work, but some formal goals. So this will be the goal that I'll adopt in this talk. So my goal will be to learn the parameters of the underlying mixture up to an additive epsilon. Now there's a slight subtlety here, which is that you can never figure out which one is component 1 and which one is component 2 because those are meaningless distinctions. But what instead is the goal is that if there's an underlying mixture of 2 Gaussians, you want to learn another mixture of 2 Gaussians so that there's some pairing of the components, either 1 goes to 1 and 2 goes to 2, or 1 goes to 2 and 2 goes to 1, so that across that pairing you get everything right. So you get the mixing weights right within an additive epsilon, you get the means right within an additive epsilon, you get the variances right within an additive epsilon. So I want to learn the mixture on a component by component basis. That'll be the goal. And the basic question, which is actually shockingly left open from this, is there a polynomial time algorithm? So if my goal is to get provably some target accuracy epsilon, and I really do get samples from a mixture of 2 Gaussians, is there an algorithm that takes poly in 1 over epsilon samples? It's not even clear what the sample complexity is of this problem. And even stronger than that, is there an algorithm that runs in some reasonable amount of time that actually finds this estimate? Yep.
So is there a reason why multiplicative epsilon gaps aren't interesting or are?
Multiplicative. So multiplicative, if you think about the mixing weight, you could never get it right multiplicatively because, if my goal is to do this in poly in 1 over epsilon samples, let's say we take 1 over epsilon samples, The point is, all you could ever estimate is the mixing weight within an additive, poly and epsilon anyways. So I think multiplicative doesn't quite make sense, but there are slightly stronger goals one could ask in terms of KL divergence between components, but that gets a little bit subtle. So this is more like trying to learn the components in a total variation sense. Was there another question? Stop me at any time. I've only had an hour and a half of sleep as Anoop so graciously volunteered for me. So in fact, I want to use this as an example to illustrate some of the different perspectives when you attack statistics and machine learning problems, because actually this problem has seen a lot of work, and it's a good place to look at what the strengths and weaknesses are of the things that have been suggested. So Pearson first studied this problem. He used the method of moments, but for reasons that we alluded to, it actually doesn't have guarantees, and there are some really fundamental questions that need to be addressed first. Yep.
And your goal, you should also specify the probability of error, I guess.
Yeah. So all the probability of error I'm going to suppress, because if I want my algorithm to succeed with probability 1 minus delta, everything I say will have a log 1 over delta, failure, the number of samples you need to take. And it won't be such an important parameter, but absolutely, because these things will only be statements that hold with some notion of high probability. So Pearson invented the method of moments. Now actually, statistics is a very interesting field, because I think you can only understand it by understanding the feuds involved. So Fisher and Pearson are credited as two of the founders of statistics. They hated each other. In fact, they had wildly different approaches to statistics, because Fisher is the one who pioneered a more information theoretic approach. So he invented the maximum likelihood estimator. There were a lot of gaps in what he suggested, and it didn't actually do what he thought it did. It took about 10 more years for him to actually prove some of the things that he'd claimed. But what he introduced was what's called the maximum likelihood estimator. So this is a natural way to think about, if I'm given samples from some distribution, how can I choose the parameters? And what the maximum likelihood offers as a way to do that is you look for the setting of the parameters that would have had the highest probability of generating the data you actually observed. So it's a simple optimization problem. You have some set of valid parameters, and your MLE estimator is just the argmax of f of xi comma theta. That's the probability of generating the sample x sub I from the parameters. And you just look for whichever set of parameters attributes the largest probability. Now, it's a little bit subtle because you have to define the valid parameters in the right way. But a lot of classical statistics is centered around this question. And what it shows is that something called consistency, that if you fix the problem size and you send the number of samples to infinity, you really do get the true parameters using the maximum likelihood estimator. In fact, it even satisfies even stronger things, that among all possible estimators, it has asymptotically the best possible variance. That's called efficient. And that's a little bit of a problematic term because we use it in a very different way in computer science, but it's called asymptotically efficient. This is actually all...
What variance are you talking about?
So this would be, so what happens is that if you fix the problem size, you send the number of samples to infinity, then in fact what the maximum likelihood converges to is it becomes a Gaussian around the true parameter, which the variance of that Gaussian is the Fisher information divided by the number of samples you get. So what's true is that actually the Kramer-Rao bound tells you that you cannot get any smaller variance than the Fisher information divided by the number of samples. So it tells you that there's nothing better than this. But there's actually a huge hole in this theory, that it's all asymptotic. So you always fix the problem size, and then you send the number of samples to infinity, because it's all based on some sort of Taylor expansion around the true point. So it doesn't actually give you any finite sample complexity bound. So a lot of people have the misconception that maximum likelihood, if you could solve it, would give you all the sample complexity bounds you could want, but that's not true. And for our purposes, the major bottleneck is also that you can't really compute it. That in almost all interesting settings, it's computationally hard.
Sorry, so when in the last slide when you were defining it,
Yep.
so how do you resolve the fact that these numbers are all zero? I mean, if you have a continuous, what is...
That's the evaluating the density function. You have to be a little careful because what you need to do is you need to lower bound the variance of each Gaussian, because otherwise what you would actually do for the MLE.
This is only for Gaussians, or?
No, this is true in general. But for Gaussians, what would go wrong with this natural definition, unless you were careful, is that you might put a variance 0 Gaussian at one point, and then it would have, infinite value there. So really, all of these theorems are about if you lower bound the variance of the Gaussians, then actually you do have consistency and asymptotic efficiency. And there's a whole industry to what are the weakest conditions you need to put on the parameter space where you can get these types of theorems to work. But it's a little bit of a digression, so I'm going to move on.
It makes sense. You can make sense of that for every.
Yeah, exactly. But the main issue is that it's computationally hard. So.
Computationally hard, not just for these 5 parameters, but you have multiple parameters.
So yes, exactly. I mean, otherwise you could, brute force and try and approximate it. But, actually a lot of the work actually happens in high dimensions, but I'll only be talking about the low dimensional case. It's in high dimensions where you really have a gap between, how much computational efficiency and sample efficiency are at odds. But that's a great question. So Teicher was actually made some really interesting progress on this. So in fact, there's the basic question of even given any number of samples, can you actually identify the components? So his basic idea is very simple to describe. He identified the actual components by thinking about the tails. So here's the idea in a nutshell. Imagine you had a mixture of two Gaussians. Well, if you look at all the way out to infinity at this distribution, then the largest variance component is going to be the one that dominates. So based on the behavior at infinity, you can find the largest variance component and then subtract it off and then recurse. So that proves identifiability, but there are some pretty big issues here, which is that it actually takes way too many samples. You're waiting for a sample all the way out into the tail. So you might be waiting for a crab whose height is negative to actually get something on the negative tail. That would be bad. Dempster, Laird, and Rubin gave what's popularly called the expectation maximization algorithm, but it's actually a heuristic for trying to compute the maximum likelihood. It has the same issues that often plague heuristics for solving non-convex problems, is that it gets stuck in local maxima, and there are all sorts of empirical studies about how this can actually happen. And the one which I'll be following a little bit more closely is there's been a lot of work within theoretical computer science over the past few decades, which the approach was through clustering. So the idea here, in a nutshell, is that, especially in high dimensions, you can imagine situations where the two Gaussian densities have very little overlap between them. So if you can take many samples and actually cluster which one came from which component, then all you have to do is output the empirical mean and empirical covariance to get a good estimate. But in fact, what I want to do is I want to ask a wildly different question, which is, what happens when the components overlap almost entirely? So no one said that the only approach to learning the parameters is actually by clustering. Can you actually learn the parameters even in situations where the components overlap significantly, like in Pearson's original case, where they overlapped enough that there was only one maximum of that distribution, right? And I'll be telling you about some joint work, actually a few years old by now, with Adam Kalai and Greg Valiant. Actually, what we studied was the n-dimensional case too, but I'm not going to cover that. In n dimensions, that's really where you get at odds with, maximum likelihood being computationally hard over all of these parameters. But the crux of it was a way to reduce to the one-dimensional case, which what I'm going to tell you is I'm going to revisit Pearson's approach from some new tools, using things like the heat equation to actually analyze Pearson's sixth moment test and show that it really does have provable guarantees, and that this ends up being one of the hearts of actually giving provable guarantees for learning even in high dimensions, which are motivated by some problems in machine learning where you really do have high dimensional mixtures. So let me ask another basic question first, just to make sure we're on the same page. So remember, the goal is to try and learn the parameters component-wise, right? Now, what I claim is that there are some cases where it's just, we just can't hope to learn the parameters. And now I can get back to Anoop's question. So there are certainly some trivial cases that we have to rule out. One case I claim is, what if the mixing weight, the first mixing weight is 0? well then, we have no hope, right? Because we never get a sample from F1, so we can't learn on a component-by-component basis. It's just a triviality. There's one more case, which this gets to a NOOPS question. What if the two Gaussians were the same? So F1 of x equals F2 of x. They were the same Gaussian, same mean, same variance. Then we can never distinguish their mixing weight, because any choice of the mixing weight is going to result in the same Gaussian. So what I'm going to do is I'm just going to assume that the mixing weight is between epsilon and 1 minus epsilon, and that the total variation distance between the two Gaussians is at least epsilon. So we're in a wildly different case than the clustering. Instead of them being almost entirely disjoint, where the total variation distance would be close to 1, we're in the case where they're almost entirely overlapping and their total variation distance is just epsilon. That ensures that if I take at least one of our epsilon samples, I get some sample in the disagreement region between them. And under just these two conditions, we're going to be able to do it. So there'll be a polynomial time, and this is where with probability 1 minus delta comes in, is that with probability at least 1 minus delta, there'll be an algorithm which learns all the parameters within an additive epsilon, and its running time and sample complexity are polynomial in 1 over epsilon, and then the log 1 over delta shows up here in terms of the error tolerance. And the best things that were known were actually Teicher's approach by going out into the tails, so they were all exponential. And I'm not going to be covering some of the later work that works for mixtures of K-Gaussians, and there's been a lot more work after that too, which I'm, again, not going to cover. But let me just tell you, yep?
But somehow you missed the simplest case where K is 1. What was known for K1?
Everything. You just, you take a bunch of samples, the mixing weight is 1, you output the empirical mean, you output the empirical variance, and you need few samples. What if what?
If
K.
is not known in advance.
Yes, so there actually what you can do is these things work in general, because imagine even if we didn't have that the mixing weights were at least epsilon, or that the total variation distance was at least epsilon, what you could do is you could either run this algorithm or run the algorithm which outputs a single Gaussian. One of those two would be correct, and then what you could do is you could do a tie breaking between them, which I'm not going to get into. The only distinction there is that there you're not learning it on a component by component basis, but you're learning the overall distribution. But if you can do this, you can actually do density estimation even if you don't know K. The other interesting thing that I want to point out is that a lot of times what you want to use algorithms for learning mixtures for is actually clustering at the end of the day. But the point is that once you learn the parameters, then you can actually do Bayes optimal clustering. Once you know the parameters, you can actually know exactly what the posterior is on which cluster generated it. So in fact, you can do clustering even in cases where there isn't separation, which is what all the previous works used. Even if, for example, it was two axes crossing each other, that'd be very easy to cluster, and then you could get it directly from these types of algorithms. Yep.
What happens when the means are the same, the variances are not?
So then, in those cases, you can still have total variation distance, at least epsilon, because if the means were identical, all you would need is that there exists a direction where the variance is non-trivially bounded. You can even replace it with epsilon over poly and n, and it doesn't matter, because it'll all translate into the runtime and sample complexity. But that's a great question, which again, I'm not going to get into because that's the high-dimensional case. But all I want to do now is just revisit Pearson's approach and tell you a cool connection. I like this one. So, in fact, I'm going to start with a much easier question because these were kind of long papers. So let's start with a much easier question. What if we were given the first 6 moments exactly? Completely exactly, right? I claim that the problem still wasn't solved then because we still had this issue. Why couldn't there be 2 different mixtures of Gaussians that had different components? So you can't match them to each other, but somehow magically match on the first 6 moments. So the question is, does this uniquely determine the parameters of the mixture up to a relabeling of the components? Because we can never tell which one's component 1, which one's component 2. So this is our question. If we take any 2 mixtures, F and F hat, well, if they're different mixtures of Gaussians, do they actually differ on at least one of their first 6 moments? And I'm going to prove that to you. So here's the idea. Let me make the problem sound really trivial first. So imagine we take f and f hat. We're just doing a thought experiment. And we take those two resulting density functions of the resulting mixtures, and we pointwise subtract them. What we get is we get some function on the real line. You know, it's positive some parts, it's negative other parts, because we're subtracting something positive from something else positive. And what I claim is the entire question boils down to how many times does this function cross the zero axis? Here I've drawn it so that it crosses at most 6 times, and I claim that's the heart of all of this. If we can prove that, then we're done. Why would we be done? Because if it crossed 0 at most 6 times, then what we could do is we could fit a degree 6 polynomial to the sign difference, so that it always agreed with the difference of their density function. What this means is whatever that polynomial is going to imply one of the first 6 moments is different. Because if we take little f of x, that's the difference in their density functions, the integral of p of x, that degree 6 polynomial that we constructed from looking at the difference, that integrates to something strictly greater than 0 against f of x. And now all I can do is write out what p of x is. It's the sum from r equals 1 to 6 of pr, the coefficient of x sub r, times xr times f of x dx. I can use triangle inequality, right? And now this becomes a familiar term because the integral of x the r against f of x, which is the difference of their two density functions, is nothing more than the difference between their rth raw moments, one of f hat. And now the game is done, right? Because if this is strictly greater than 0, there clearly has to be one of the first 6 moments must be 0 too. If they were all 0, the right-hand side would be 0 and we'd have a contradiction. So the entire game comes down to this sort of embarrassing sounding question of if I take one mixture of two Gaussians and pointwise subtract another, how many times does it cross the 0 axis? This is ignoring all issues about, you know, how noticeably large this correlation is. That's technical work that needs to be done, but it can be done. But let me prove the remainder now. I'll prove a more general proposition. So here's the proposition. So imagine we take any linear combination of k Gaussians. So we take any combination, any way to sum them up, where these alpha sub i's can now be positive or negative if you want, and you add up and subtract a total of k of them. What I claim is that if the resulting function f of x is not identically 0, then it crosses the 0 axis at most 2k minus 2 times. So for example, in our setting where we took f and we subtracted f hat, that was actually a linear combination of 4 Gaussians. So k would be 4, and we'd get at most 6 0 crossings, and we'd show that Pearson's 6th moment test works, right? And we're going to do this through the heat equation. So here's the idea, is actually there's a beautiful connection between Gaussians and the heat equation. So just to remind you, in case it's been a while like it has been for me since you've seen differential equations, well, in the standard, problem, in the heat equation, you start off with a one-dimensional infinite rod with some constant, kappa. It's the permittivity of energy or something like this. In any case, what you start off with is you start off with some initial heat profile along the infinite rod. Let's call that f of x. And a very natural question that you ask in differential equations is, what is the solution look like at some later time t? Now, in fact, you could solve it just by, if you were actually in some differential equations class, they would give you some f of x and you'd have to churn through it. But there's a really simple way to describe what the solution is using a Gaussian. The key word is that the code is that the Gaussian is the Green's function of the heat equation. But what that means is if you want to know what the value at x is at some later time t, all it is you take the average value of f of x plus z at time 0, where z is a Gaussian random variable. And the variance of that Gaussian random variable, sigma squared, depends on the time. So as you increase the time, you're taking an average over a wider and wider space, and that's the mechanism by which allowing the heat equation to run forwards actually smooths out a function. So this is called convolution, where f of x comma t is literally this value. You start off with just the value f of x at time 0, and then you convolve it by a Gaussian. That's just the operation of creating the new value as the average over a Gaussian window around it. And what we're going to do is instead of running the heat equation forwards, we're going to run it backwards. So the idea is that we're going to pull out a random theorem from the 1970s, from Hummel and Guidas. Yep.
Why is there no t on the right hand? Oh, sigma squared has a t.
Yeah. So sigma squared depends on t, and it depends on kappa. So we're going to pull out this random theorem, and then we'll be done. So it turns out, and it's a longer story why this is true, but if you have any function that's analytic and has at most n zeros, then actually convolving by a Gaussian, because it corresponds to running the heat equation forward, has a lot of intuitive properties. One of them is that it doesn't increase the number of zero crossings. So this is actually much more natural than it sounds, because when you think about the heat profile along the real line, we know that running time forwards is smoothing it out. So if you're smoothing it out, you should never create a new local minima, because as soon as you tried to, you'd have a new diffusive pressure to try and pull it back up. And if you tried to create a new local maxima, there'd be a pressure to pull it back down. And that's actually the same mechanism by which you can't actually increase the number of zero crossings. So now we can, so convolving by a Gaussian does not increase the number of zero crossings. And also we're going to use the following fact that when you convolve two Gaussians, you get another Gaussian. And in fact, what you get is just the sum of the means and the sum of the variances. You could get this, for example, from the central limit theorem. So now we're going to prove this proposition and return to it. And we're going to prove it by induction, and I'm just going to show you one case. Let's assume we've proved it for k equals 3, that all linear combinations of at most 3 Gaussians have at most 4 zero crossings. And I'm going to prove that when you go to k equals 4, you only have at most 6. And the proof will just be by picture. So we take our original linear combination of 4 Gaussians, we added 2, we subtracted 2. And all I'm going to do is I'm going to take the thinnest Gaussian. Whatever that variance is, I'm going to run the heat equation backwards until that Gaussian becomes a delta function. So I'm just subtracting something from the variance of all of the Gaussians. Now let me ignore that delta function. I now have a linear combination of 3 Gaussians, so I know it has at most 4 zero crossings. But when I add back in the delta function, how many more zeros can I add? At most 2. 1 on the way up and 1 on the way down, because it's all localized around that delta function. You have to do a little bit, you have to be precise in a real analysis sense to get this to work, because you don't actually make it a delta function, you make it arbitrarily close to 1. But in any case, now the entire point is we can apply the theorem of Hummel and Guidas, get our original linear combination of 4 Gaussians by convolving by a Gaussian of the variance that we subtracted off, but that only smooths things out, so it doesn't increase the number of zero crossings. So hence the number of zero crossings is at most 6. That implies 6 moments suffice. That tells us that Pearson's approach, at least if you were given arbitrarily good approximation of the right-hand side, would work. And it turns out that actually using a bit more work and being quantitative about these things, you can actually prove an actual stability statement that if you get the first 6 moments, so what this is really saying is that, you know, here's an abstraction of it, is that if you let theta be the true parameters, well then remember that we have mr of theta, which is actually the rth raw moment. What it's saying is that the only choice of valid parameters, theta hat, that actually meet that system of polynomial equations are the true parameters, or one where you've swapped which one is Gaussian 1 and which one's Gaussian 2. And the last thing is that it turns out that systems of polynomial equations are stable in a general sense. So by actually making some of those arguments quantitative, you can show that if you're within epsilon to the c of the first 6 moments, that implies your epsilon close in the true parameters. So this now gives us a, hence close enough estimates the first 6 moments. If you are close enough, that implies that you really are close to the true parameters. So now our univariate algorithm is just a slight variant of Pearson's. It's basically the same thing. You take a bunch of samples, a lot more than Pearson did, and you compute these m tilde subrs, and you compute them so that they're close within epsilon to the c over 2. Then you compute any theta hat so that mr of theta hat is close to m tilde sub r for each of the 1 through 6. How close? Within epsilon to the c over 2. This implies that whatever theta hat you found is within epsilon to the c of each of the first 6 moments, which implies that it's not just close in moments, but epsilon close in parameters too, because of the polynomial relationship we proved between how the difference in distance in parameters relates to the distance in moments. So this is actually how you can get Pearson's approach to rigorously work and get a polynomial time algorithm, even when it wasn't clear whether there were finite sample complexity bounds for these things. Yeah?
What's the constant C?
We've been made fun of perpetually for this. We proved 300,000. It's been improved to 12, but it's actually 12. So it's not a good constant. It actually is, it's polynomial, but it really does need to be a high degree polynomial. Was there another question?
So, beautiful. Nice idea. It's not clear how this generalizes to higher dimensions, because zero constant,
Yeah, so it turns out, I mean, that's a longer talk, but it turns out in high dimensions what you can do is when you project the high dimensional mixture onto some direction, that gives you a univariate mixture of 2 Gaussians. If you learn the parameters in that direction, it would give you constraints on the high dimensional parameters. There's an issue of how do you pair up the projections across each other, but there are ways to do that. There are ways to bound the condition numbers of those systems to churn it all the way through. And actually, to address your question about how bad the 300,000 is, I'll add as a mea culpa, I'll show you an even worse constant, which we can do but is more general, which I think is fun, is we can actually take a view from algebraic geometry, which is kind of fun. So this follows Belkin and Sinha, who had this really nice approach to it, which abstracts it in the following way. So let's do the same thing that we did, but in a more general algebraic geometry language. I don't know that much about it either, so I'll spare all the details. I'll just tell you what you need to know. So the idea is that actually under pretty tame conditions, if you have 2 different parameters, so you have some parametric family, well, if you have 2 different parameters, theta and theta hat, in such a way that they agree on all of their moments, not just the first 1 through 6, but all of them, all of them, all of them, under pretty tame conditions, that actually implies the 2 density functions are the same. So all you need is that the moment generating function converges in a neighborhood around 0. But we'll say that a family distribution is a polynomial family if this condition holds. If matching all of the moments implies you're the same density function. Very tame condition, because it certainly applies to things like mixtures of Gaussians and even beyond that. But now the idea is the following. So this is where the algebraic geometry is going to kick in. Let's do the following trick. Remember, we had mr of theta. Well, let me create a new set of formal variables, theta hat. These are just disjoint sets of variables. So we had 5 before, and we have 5 more. So let me create a new polynomial, qr, of theta comma theta hat. That's the difference between these 2 formal polynomials and these variables. And it turns out, from Hilbert's basis theorem, that the following is true. Let me tell you what this means. So in algebraic geometry, you can create something called an ideal, which is some family of polynomials generated by some base fixed set of polynomials. And Hilbert's basis theorem tells you that a sequence of ideals can't continue to be strictly increasing forever. At some point, it has to stop. And what that means when it stops is that you can write every later thing as some polynomial combination of the older things. So it tells you that there is some n, so that you can write any, for any qn plus j, so anything you go beyond the nth moment, you can write that as some polynomial coefficients in the parameters times the lower order qr of theta comma theta hats. This is just the direct consequence of Hilbert's basis theorem, but now we get an even worse constant because this is provably ineffective. So you know that n is finite, but you cannot prove a finite bound on n. But what this means then, if we abstract it, is if you agree on the first n moments, whatever that n is, it's some finite value for each of these polynomial families, well, the fact that they're all 0, well, by virtue of this expression up here, then, implies that everything after n is also 0 in terms of their difference. So if you match on the first n, you continue to match. And that, through the fact that we have a polynomial family, implies that the 2 density functions are the same too. So there's actually a way to get all of this out of algebraic geometry, but in a way that you know there's a polynomial time algorithm, but you don't know the degree of the polynomial, which is kind of amusing. So it yields a general connection between method and moments, but there's no effective bounds on n for this. All right, so I think I want to quickly summarize what's going on, what we talked about. I'm going to talk about some of these issues about algorithms for statistical problems and for machine learning problems through all the other tutorials. Those will be a little bit more tutorially and not focus on individual problems. But a quick summary is, so we gave first efficient algorithms for learning mixtures of Gaussians, that there are very interesting things in trying to make these heuristics effective and actually getting finite sample complexity bounds. And one of the interesting things is that computational intractability, I claim, is everywhere in statistics and machine learning. That's because the underpinnings of the field, if you go back to people like Fisher, their approach was the maximum likelihood estimator. That's because they were really in a sample-starved time when they cared about actually getting the absolute most out of their number of samples that they were given. And they were anyways doing their computations by hand, and Pearson is clearly way better at doing computations by hand than all of us are, given what he did. But now, there are much more interesting questions about when you move to high-dimensional problems, computing the maximum likelihood is not so apparent. So what if it converges the true parameter at the best possible asymptotic rate? That doesn't really tell you whether there are computationally efficient estimators that also converge at some reasonable rate. So for many of these questions, at face value, they're computationally hard because maximum likelihood is NP hard. But that doesn't mean in these average case problems that you can't still do almost as well as if you could. So most of the approaches also are kind of heuristic for a lot of these problems. They rely on things like the EM algorithm, which really can and do get stuck in local optima. I think there's a really interesting agenda and line of attack here where things like theoretical computer science can suggest completely new algorithms that don't fall into these standard pitfalls. Sometimes they end up with polynomials where the degree is 300,000. Sometimes they don't. And so can we design new algorithms for some of the fundamental problems in these fields? So the things that I'll talk about in some of the other tutorials, I'm going to tell you about tensor decompositions and their applications in parametric inference. I'll tell you about linear inverse problems and connections to SDPs. And then I think I'll tell you about community detection, but I still have to write that one, so time permitting. And that's it. So thanks for your attention. Any questions you guys have? Thanks.
Actually, many solutions which all give something which are very close, are these solutions themselves close, or are they far apart? Are they well
The
separate?
solutions themselves are close in total variation distance of the mixture,
I see.
but they're not close in parameter distance.
I see.
So that's actually the issue with the lower bound.
I see.
Sorry, just 1 second. Yeah. Yeah, my question is about computing, so solving the equations for the sixth moment methods. So which algorithm do you use exactly, let's say, for the sixth?
So here, since it's in low dimensions, you can brute force, and that's fine.
And
now,
is it stable?
Yeah. So they're actually fairly general. So we proved a fairly direct way for stability for these things, but they're actually more, more general ways, which yield even worse bounds, which are called Voyashevich inequalities. So the thing is that in algebraic geometry, some things are effective and some things aren't. So things like Hilbert's basis theorem are not effective, but things like quantifier elimination are. So the idea is that sometimes you can think about why systems of polynomial equations are stable, because you can project out the noise, variables, and then you still have something defined by polynomials, and that's the reason why you get some polynomial stability in the left-hand sides and how they translate to the parameters. But there are actually many ways to get to these Voyashevich inequalities, but that's perhaps a longer discussion.
Okay, I see.
Sorry, I'm just hogging the mic. I'm curious, were there two genetically different species of crabs? Or?
Oh, there were like 9, actually.
Oh, I see.
So it was quite a few, actually.
I see. So the biologist went back
Yeah.
and...
In fact, the thing I've never really figured out, I tried to get it out of that paper, was why he chose the ratio of height to circumference. It had something to do with like a biological constant that he thought was roughly fixed for it, but I've never quite figured out that part.
okay.
But it's a really amazing paper.
But it was really two different crabs. Biologists, what they found later.
Oh, they found like 9 crabs. So they found certainly at least 2, but...
Other questions?
So, about Karl and Moitra and Valiant algorithm, is it possible to find K given samples, enough samples?
So that actually falls into the parameter learning lower bounds, that what you can do is you can take these algorithms, which the extensions have exponential and K dependence, but they need to for parameter learning. And those types of things, you could actually remove knowledge of K and still get them to work. Now, the issue is that if you don't want exponential and K dependence, then some of the lower bounds that we have for parameter learning directly give lower bounds against that. Because what they really are is they're a single Gaussian that can be very well approximated by a mixture of K Gaussians. That's actually, I mean, it's a pretty easy construction to describe. So, the point is if you take 2 Gaussians and you convolve them, you get a wider Gaussian. So what you instead do is you convolve this by a discretized Gaussian. And this ends up being very close to the original Gaussian. So there's a way that you can actually interpret what this is doing in Fourier space by, so convolution goes to multiplication. So instead of pointwise multiplying 2 Gaussians, what you're really doing is you're pointwise multiplying this guy and something else. But a comb function, this is really the pointwise product of a Gaussian and a comb. And a comb goes to a 1 over with comb. So it's really like a Gaussian, which is convolved by a comb, and then you're hitting it with another Gaussian, so it damps all the other things going on. And that's why it's actually close to the original thing. But what that directly gives you is it gives you something which is actually a mixture of K Gaussians. It's just that it incredibly well simulates, exponentially in K close, a single Gaussian. So if you wanted to ask questions like, can you avoid knowing K or can you learn it? Yes, with exponential and K dependence. But if you want to avoid that, someone would have to tell me how to avoid these types of cases. There would have to be some way to rule out this sort of triviality and corner case.
Any other questions? If not, let's thank Ankur again.